Hello, everybody, and welcome to the second part of how deep learning works. So, if you do not understand what is here, please watch the first video where I broke it all down. And so, for this video, the only change that I made was just to change this to a decimal point because ideally the weight should be between 0 and 1. So I want to make this as realistic and as close to how it really works as possible. So that's why I just changed it from 2 to 0.2, from 4 to 0.4, and then I updated the values. So and that's it. So now let's continue from where we stopped. Our example was and still is a simple neural network for binary classification to distinguish between two dog breeds, Bulldog and German Shepherd. So now let's say our network has all this random weights and biases. So by the way, the neural network starts with randomly assigning values to the weights and to the biases. There are techniques for this that just helps with the random assigning of values, but that's not the focus of this topic. So now imagine we already have weights for each single one of them, each single connection, and we already had the biases, and we already have all of the weighted sum of inputs and all the calculation. And during the process, the training process, it's trained one image at a time. So one image is put into the neural network from the input layer. So remember from our previous example, we're assuming that each image is a 2 by 2 pixel. So in total 4 pixels, as we have 4 neurons at the input layer here. And so let's say one image of a bulldog now is fed into the neuron, into the neural network from the input layer neurons, and its weights that have been randomly assigned, the bias added to it, and it goes on to add new weights here, and then it adds the bias and the neurons, and then it gives an output. So let's say, for example, our user, what code do I use? Use this. So for example, our output layer gives a prediction or classification or classifies the bulldog and says, okay, for bulldog, it gives it a 0.4 and then says German Shepherd, it gives it an output of 0.3, for example. So just to add at this point here that the output of all of the numbers or the value of all of the output neurons, when you sum it up, it should sum up to 1. But because this is a very simplified example and I'm just using only two output layer neurons, so I'm not really following that rule, because if I follow it, it's gonna defeat the calculation I'm trying to do and the example. So let's just assume that everything sums up to 1. Just bear with me for that. So, and remember, the correct image is actually bulldog. So it actually got it correctly. It predicted it correctly. But this is not a high confidence value. We want it to be really confident. So yes, it got it correctly, but It's not confident. So the question is, how do we increase the neural network's confidence in the output value? We do this by using something called cost function. Cost function. Let me write it here. What is a cost function? A cost function is a mathematical operation that differentiates the difference between the network's output or the predicted output and the actual answer to determine the accuracy of the network. Let me say that again in case you didn't get it. I could write it down, but it's kind of long, so. A cost function is a mathematical operation that compares the network's output with the actual answer to determine how accurate the neural network is. So how does this work? How do you calculate the cost function? So the cost function, see it as error function. It makes the neural network pay for every error it makes. That's why it's called the cost function. So how do we calculate the cost function? It's by differentiating or calculating the differences between each right answer and wrong answer and dividing it by the number of the values. Let me explain. So we know that the output value for the prediction of Bulldog is 0.4, but we want to nudge it. We want to nudge a plus 0.6 so that it gets to 1. So we say 0.6 because we want to nudge it. So 0.6, I could say plus 0.6. Let me say plus 0.6 so you get the entire gist of what I'm saying. Want to nudge it with a 0.06. And then this, we want to nudge it with a minus 0.3 because we want it to get to 0 and want this to get to 1 as much as possible. So minus 0.3 divided by the number of the values, which is 2, right? Because we have 2 output neurons. So 2. Now this would be 0.3 divided, I wanted to use calculator, but 0.3 divided by 2, which I believe is C. Permit me to use my calculator. 0.3 divided by 2.15. I guess that's much. I just wanted to be sure, which would be right here. So this is a cost function. How to calculate the cost function for, let me specify, this is for just one training sample now. For one training sample. This is just one. One training sample means one instance of the data. So for example, if I have 1,000 images, so this is literally just one of 1,000. So I have to do this for all of the 1,000 images. Then when I do that, I then sum up all. So for example, I have another, I just want to come up with something. So this cost function basically is the sum of all average errors. So this formula you see here is the average error. So if I, for example, I have another, let me just add one more. So let me just add one more training sample. So we just work with like 2 training samples since we cannot do 1000. So I'll just say maybe another training sample, the result, nudging them will be like 0.4 minus 0.23 divided by 2 would be calculator 0.4 minus 0.23 divided by 2 is 0.085. So now the overall, let me say, I wanted to move this up, but let me just say the overall cost function let me call this average errors and then move this. So 1 second. For clarity's sake, you understand what I'm doing in a second. It's as fast as possible. Okay, so this is average error. Let me put this on one line as well. So the one we just know, yeah, it's still the same. I just want to take out this first step. We still know it's still 0.3 divided by 2. Let's just put the answer here, 0.15. And want to be as clear as possible, so just stay with me. Training error. So let me say training error for sample 1. Okay, let me put it here. Training sample 1. Remember, training sample is another word for an instance of a data set. So let's say training sample 1. Yeah, okay, I'm glad it's getting clearer now. So let me just move this up a bit. 0.4 minus 0.23 divided by 2, 0.085. Okay, let's have 3. Let's have 3 samples. So let's just tweak this up a bit and say maybe this should be 0.7. So let's just call this 0.7. I'll call this 0.4. Yeah. Or say 0.3. 0.4 divided by 2, 0.2. So average error, training sample 2, stay with me, average error, training sample 3, and it goes on and on and on. This is how the machine calculates for if it's 1000 data points or data sets, goes on all the way to training sample 1000. So then afterwards, it calculates the overall, let me use another color. It calculates the overall, trying to see if I should use pink, but let me just use orange. So overall cost function by simply adding up all this 0.15 plus 0.2 plus 0.085, which would be I was just thinking, I hope this isn't too tiny. 0.15 plus 0.2 plus 0.085, that's 0. So for our example here, this is our overall cost function. Basically, it reflects how accurate our neural network is. But the goal is to nudge our overall cost function to 0 or as close as possible as it could get to 0. For example, maybe 0.01 and so on. Now the question is, how then do you do this? How do you reduce the cost function? Because this represents how the sum of all the errors made by the neural network. So we really want to make sure that the error is as close to 0 as possible. For example, 0.01. So how do we do this? We do this through something called backpropagation. Let me just use, sorry, my pen fell down, so let me just draw this. Okay, so we do this through something called backpropagation of errors. It's also called backpropagation for short. So now, this is where it gets really interesting. Stay with me. So this backpropagation, it's literally, okay, you know what? Before I explain what backpropagation is, let me actually write down what it uses. So backpropagation does what it does through something called the chain rule, and also something called gradient descent. Okay, so first of all, the chain rule helps the network to identify what each weight contributes to the cost. I should write this down. Let me write it down. Let me put some space in between so that I could actually write this down for your reference. Yeah, Yep. So let me give some space. Okay. Let me give space. So I'm already here. So the chain rule helps the network or the neural network identify what each weight contributes to the costs. That's what the chain rule does. Now, back to what gradient descent. I'm gonna tie all of this together. Stay with me. Gradient descent. Gradient descent helps the neural network know the direction with which to adjust the weight direction to which does better. The weight bias. Okay, we're tying it up closely. So, I hope this is not confused with this. Yeah, so basically, the gradient descent helps the neural network know the direction to which to adjust the weight and bias. Now, let me tie all this up together. So now, the chain rule, because when you find the cost function, one thing about the cost function, it shows the overall performance of the neural network, but it doesn't specify how each neuron and weights are performing or are contributing to the performance or otherwise of this neural network. So the question is, how then does the network correct its errors to improve its performance? It uses something called the chain rule. So the chain rule helps the neural network identify, how each weight and each neuron contributes to the cost or error. When you see cost, also think error. So contributes to the cost or the error. So once the neural network has identified, okay, this weight is contributing such and so percentage to the error. Then the gradient descent helps the neural network know which direction to adjust it. So okay, then increase it or decrease it. So the goal is to adjust it to the direction with which the error or cost can be reduced to the greatest. minimum. So what does this backpropagation mean? Imagine the name backpropagation. So backpropagation of errors, it starts, so this is the output. It starts with the accurate output, then goes to the connections to this neuron, and also looks at the bias. It modifies the bias, modifies the weights of all the connections to the neurons, and sees how it contributes to the output. Then it goes on to the neurons at the hidden layer, modifies the bias and the weights connected to the neuron, sees how it contributes to the output, and then if there was another hidden layer, it will do so, and same with it. But here we only have one hidden layer, so it stops at this, the weights, stops at the input layer, where the input layer gives its weights from weights to the hidden layer, and also stops right here at the weight level. So that's why it's called backpropagation. It literally starts from the output layer neuron, modifies the bias, and then modifies the weights, sees how it contributes to the output, goes to the hidden layer neurons, modifies the bias, modifies the weights, see how it contributes to the output. Here, that's where we stop because we only have one hidden layer. That's what it's called. That's why it's called backpropagation of errors. And so once it does that, it goes to the next neuron, the next output layer neuron, which in this case is the second one and the last one we have. It does the same thing until it reaches the input layer level. And then once it has modified all the way, it moves forward again. It starts the process again. As we discussed in the first video, it starts the process again, calculates the weights, adds the bias or adds a negative bias, whatever it is, adds the weight again, like that, and then sees the output. It does this again and again until it reaches a convergence. And convergence in this case meaning that it's able to predict our Bulldog with a very high percentage or high accuracy or confidence level, maybe 0.9, 0.99, and then the wrong one would be like 0.01, like that. And let me write a definition for backpropagation of errors before we end this video. Okay, so starting from then to yeah, so is there anything else I want to touch on? No, so actually, there you have it. This is how deep learning works, simplified. Let me know your comments and if you have any questions in the comment section. So the next video, continuing on teaching about AI, machine learning, and deep learning will be upper week, because next week my interview or podcast interview with a lawyer in the field of AI would be dropping. But you could also feel free to watch that as well. See you. Take care and bye bye.